Back to Hogwarts. Take one. 3, 2, 1, action.
If we say HP, what do you think of?
We are first year students of the class of liceo scientifico, Corridoni-Campana Hogwarts, and now we are going
back to Hogwarts looking for some
real magic.
Welcome to everyone. Today we're going to show you some experiments about geometrical optics. The point of geometrical optics is that a ray travels in a straight line. Have fun.
The experiment is composed by a lens and the rays that comes from the windows, and I'll find the focal point of the lens.
If we have a bundle of rays parallel to the lens, the point where they converge the rays is called the focal point that we indicate it with F.
Okay. To get a parallel bundle of rays, you can simply consider a source of light which is very far away from the lens.
For doing this experiment, we are going to use the light of the sun and converging lens, but we use ordinary lens. And for the screen, we are using the wall of the room, and for measure the distance, we are going to use a tape meter.
So once you have the lens, you need to move the lens until you have a sharp image, and when it's also on focus, the only thing you need to do is measure the distance from the lens to the image, and that's the focal point of the lens.
The experimental setup consisting of a light source, for example a lamp, a converging lens, a sheet of paper that we can use as a mobile screen, and a ruler or a tape meter in case we want to measure P and Q.
Put the light source and the lens on a table at a distant rate than to the double of the focal length.
Hold the sheet in your hand and move it until a sharp inverted image on the source appears on it. You can now probably the image. You probably figure out by using rice
If you put the light source in a distance greater than 2 times the focal point, you get a small inverted and real image. If you put it at precisely 2 times the focal point, you get a inverted image of the same size as the object. If you put it in a distance smaller than the focal point, you get a virtual, bigger and straight image. Instead, if you put it directly on a focal point, you don't get an image because the rays don't converge.
The pinhole camera is one of the simplest optical equipment. It is just a box with a small hole on one side, and in the other side there is a translucent screen. The hole should be small enough to be represented by a point, its dimension. Its dimension should be negligible if compared with the dimension of light source.
Each point of an extended light source, a lamp for example, is emitting a lot of rays, but ideally only one of them passes through the hole and reaches the screen. That's why we got a sharp image of the source on the screen.
If the hole gets bigger, the image won't be in focus anymore. In fact, several rays coming from the same point of the light source will be able to pass through the hole these color rays will reach the screen and produce a spot instead of a point. The image will be out of focus, and if the hole is big enough, on the screen you will see a spot with the same shape of the hole.
If the hole is too small, the image will be sharp but very dim because of the small amount of rays passing through the hole. So real pinhole cameras, like our eyes or the cameras we use to take pictures, tend to make a compromise between these two factors and adopt a proper dimension for the hole. As you can find out by tracing the rays, the image will be always real and inverted. It may be enlarged or diminished depending on the distance between the screen and the hole, that is called the focal length of the pinhole camera.
The experimental setup consists of a pinhole camera, and in order, if you want to make one, you need a paper box and a piece of translucent paper, like tracing or baking paper, a search light, like a lamp, and a dark environment.
In front of the pinhole camera with a big hole, you will see a point of the hole. If you put the lamp in front of the small hole, you will see an inverted image of the lamp.
Are two parabolic mirrors arranged in order to overlay the optical axis along the vertical direction. The upper mirror has a hole in the middle, so the lower mirror is located above the focus of the upper mirror.
An object is placed on the focus F1 of the upper mirror, so its rays after hitting the upper mirror are reflected downwards in a vertical direction.
This vertical direction is also parallel to the optical axis of the lower mirror, so these rays hit the lower mirror.
As a consequence, the rays converge on the focal point of the lower mirror, and then they exit through the upper hole in order to get to the observer side.
The observer has his eyes interpret the light as straight rays coming from a source, and will interpret those rays as coming from an object placed on the hole, and we see the mirage is.
In the end, we learn an important lesson, that magic can be real